So far, we have discussed large-scale structure in the sense of where the galaxies are, but where are they moving? So let's find out. What we mean by the term of peculiar velocity for galaxies is a velocity component in addition to their Hubble flow due to the expansion of the universe. So in other words, if the galaxy was at rest compared to, say, microwave background in co-moving coordinates, it will have peculiar velocity of 0. The only component we could observe for it would be due to the radial expansion of the universe. Now, even though velocities are three-dimensional vectors, we can only observe the radial component due to the velocity because galaxies move way too slow on the sky to actually be able to measure that. So if you're interested in some aspect of cosmological expansion, then these peculiar velocities are like velocity noise atop of the actual Hubble flow signal. And so, for example, if you're plotting a Hubble diagram, which is some form of distance versus redshift, you can have errors in distances, but you can also have what's not really an error in velocity, but a shift. In other words, it's error in a sense if you assume that velocity is only due to the expansion of the universe. And the origin of this is obvious. If there is a large-scale density field, there has to be a large-scale peculiar velocity field. A reason for this is that during the age of the universe, galaxies will fall towards the nearest massive structures to them, acquire velocity gradually from 0 to whatever they have today. So in some sense, the pattern of peculiar velocities has to reflect a pattern of the density distribution. Now there is one peculiar velocity, some people would say only one, which we know with a great deal of precision, and this is our motion relative to the cosmic microwave background. This causes a dipole. Cosmic microwave background is a little hotter in the direction that we're moving to, and the velocity is about 620 kilometers per second in a particular direction in the sky. It turns out this is fairly commensurate with typical peculiar velocities in a large-scale structure around us today, or for galaxies maybe a little less, a couple hundred kilometers per second. But Virgo cluster has Hubble recession velocity of only like 1,000 or 1,200 kilometers per second. So a peculiar velocity component like this could really make a difference. So we have a simple equation that relates total observed velocity, the distance to the galaxy, Hubble constant, and its peculiar velocity. So we can easily measure a total velocity, that's the redshift. We can ostensibly measure Hubble constant. But then the tricky part is the distances. So the errors in estimation of distances to galaxies will map directly into the errors in estimates of their peculiar velocities. You may recall that there is a number of distance indicators for galaxies which we can use to compute their distances. They're not given by the redshift, but each one of them has its intrinsic scatter, and each one of them would then yield errors in the estimates of the peculiar velocity. For most part, peculiar velocities are commensurate with Hubble velocities only in the nearest universe. And if we go further, say, beyond local supercluster, most of the velocity is due to Hubble expansion. But the fractional error of the Hubble expansion times that velocity gives you the absolute error of the peculiar velocity. And so the sensitivity is much higher. Sometimes we measure distances not to individual galaxies, but clusters to which they belong. In that way, we can average measurement over a large number of galaxies and improve the corresponding measurement for the entire cluster. So measuring distances to galaxies is very tricky, as you probably recall from an earlier chapter. But there is another way in which we can measure peculiar velocities, and that is from redshift surveys themselves. Now, first, remember about the redshift space. We observe some structure of galaxies in an individual galaxy, and if it is a very massive structure, it's virialized, like core of a rich cluster, galaxies will have their own thermal velocity due to the potential well of the cluster itself. Now, we do not measure the component that's tangential in the sky, but the radial component will be there. And so the higher the velocity dispersion in the cluster, the more will galaxies scatter in velocity around their true Hubble expansion value. And if you assume naively that that measured velocity is only Hubble velocity and convert into distance, then a spherical cluster will become elongated along the line of sight due to these peculiar components. That is known as the finger of God effect. On the other hand, if we are still in a linear regime, that is low density contrast, galaxies are slowly falling towards some filament or sheet, then the opposite will happen. There will be some intrinsic width of that filament on the sky, say perpendicular to our line of sight. But galaxies falling towards it on our side will acquire a little extra velocity. They'll look like they're a little further away than they really are. Galaxies on the other side are falling back, so they will look like they're a little closer than they really are. The net effect of that is that filament looks thinner in the radial direction than it really is. So statistically, you can do this for whole ensemble of galaxies using big redshift survey. And what's shown here is a density plot that corresponds to radial component of the distance as well as the orthogonal component, which you can measure from angular separation in the sky. So note there are two features to this. At very small angular separations, which will largely be for galaxies that really are physically close together, like in clusters of galaxies, you see a vertical elongation, the finger of God effect. But for most of the rest, you see flattening of the distribution, which normally should be spherical. The flattening is due to that linear infall into the structures along the line of sight. So how can we measure peculiar velocities when all we're measuring are total velocities in a redshift survey? It goes like this. You assume first that galaxies are where their observed velocities imply. That gives you a first approximation to the density distribution in space. Then, making some assumptions about mass-to-light ratios and dark matter and so on, you figure out how much would galaxies there would have acquired in terms of peculiar velocities through the history of the universe. And then you subtract that component from the original measured velocity. You reevaluate the density field at that point and repeat this several times. At that point, you should have, statistically at least, a good separation between true distribution in space and the peculiar velocity distribution. So you can do this without measurement of distances altogether. However, the problem is that there is a model dependence. You have to assume something about, say, amounts of dark matter in these structures and so on. So here is the local kinematics of the large-scale structure plot. We are falling towards Virgo with a speed of about 270 kilometers per second. The whole local supercluster is moving in the direction of Hydra Centaurus supercluster at a somewhat higher speed. And things may actually go even beyond that. So here is a map of galaxies in the sky. The band in the middle is the galactic plane, the zone of avoidance. And you can see a large-scale structure with many elements labeled. The hatched blue area on the left corresponds to rough location of the masses or mass responsible for our peculiar velocity, which was called the Great Attractor for a period of time, but I think now people refer to it by its original name of the Hydra Centaurus supercluster. So I mentioned that given a peculiar velocity field, you can derive the underlying density field that must be responsible for it. And here are examples of what it might look like in projection to the supergalactic plane. Of course, the real thing is in 3 dimensions. But here in this here in this landscape, the height corresponds to the local density. And the plot on the upper right shows the vector field of velocities that correspond to this density distribution. So we're in the middle of this map, in a valley. A little bump next to us is the local supercluster, and a much bigger mountain to the left is the Great Attractor. The large mountain on the other side is Perseus Pisces supercluster. And so if you look at the velocity field just above it, you'll see that there is overall flow towards these two massive structures. You can do this with any redshift survey, and it was indeed done so. That's good because these are tricky measurements, and it's good to do them as many independent times as possible. You may remember there was a survey based on IRAS catalog of galaxies, which is called PSEZ survey, and this is what their density distribution of galaxy looks like projected on the supergalactic plane. And here is what the corresponding velocity field's like. There are again two huge attractors. There is a big one, Hydra Centaurus, and then there is one on the other side, the Perseus Pisces supercluster. But the flow may continue. Deeper redshift surveys suggested that in fact this whole local volume is moving towards an even larger mass concentration, a couple hundred megaparsecs out, called the Shapley concentration of clusters, named so because Carol Shapley noticed that there seems to be excess number of clusters in that area of the sky. The picture here shows where some of those clusters are in projection, and they're also close by and large in 3 dimensions. And that's about as large density fluctuation that can cause peculiar velocities as you expect. Not everybody agrees with that though. Sasha Koshlinsky and collaborators used distant clusters of galaxies, measuring their distances from X-ray and so on, and they concluded that the flow continues even beyond. They called it the dark flow. At the face value, this seemed to be in contradiction with our understanding of structure formation because we simply don't expect that there will be a substantial velocity buildup due to the structures larger than a couple hundred megaparsecs. But if this is true, then there must be an explanation like that. One possibility that people have discussed is that, in fact, there is a huge mass concentration beyond the horizon of our universe. Due to the inflation, we are close at one point, but now we don't see it. But there is an overall gradient in gravitational potential in that direction, and some people call it the tilted universe. The universe is rolling downhill towards this unseen, hypothetical, huge mass concentration. And I'll emphasize the word hypothetical. So to summarize, measuring peculiar velocity is very difficult. If you have to use distances to subtract them directly from observed Hubble flow, then errors in distances are very important. And systematic errors that could be present in distance indicator relations, like their 0 point may be a function of something, could really play havoc with that. The other possibility is an internally self-consistent solution from a redshift survey alone, but that requires you to make an assumption about underlying mass distribution model of sort. We are falling towards Virgo cluster at 200 or 300 kilometers per second, and local supercluster is falling towards the Hydra Centaurus at about 400 or 500 kilometers per second, and maybe the whole thing is moving towards an even larger concentration. But most people think that our net peculiar velocity, the one that we measure with respect to the cosmic microwave background, is pretty much due to the masses within the 50 megaparsecs per mass or so, just not too far from local supercluster. This is not entirely settled, but it is an emerging consensus view. Another important result from analysis like this is that it appears that on large scales, indeed, the mass and the light are distributed pretty much in the same way. Galaxies are where the dark matter is. This is not the case at small scales, like scales of galaxies, where there is a real separation. But on scales of large-scale structure, this is true. And we know this because the pattern of peculiar velocities we see is exactly what we'd expect from the density field if the dark matter was associated with galaxies, if it was in the same general vicinity. Next time, we will talk about phenomenon of biasing and how is clustering evolving in time.